I can't say his last name. It's like Mr. C or something. No. My substitute coming in for me. He used to be. Yeah. I hope so. I mean, I haven't seen him teach or do anything, but I've heard he's okay. He was down here at the beginning of the year for Mrs. I think her name is Paff. That's how you pronounce it. Our new math teacher. He was in there initially, but now he's kind of been a sub around. I don't know. He's planning on coming in though to like see how things go and maybe practice a few things. So we'll see. All right. So up to this point with polynomials, okay, we've been looking at factoring techniques, a little bit of a review. We've been looking at above x-axis, below x-axis to analyze those inequalities for polynomials. We're going to take a look at two big kind of theorems in this section. We'll get to one today and the other one tomorrow. But before we can get to those theorems, we're going to practice synthetic division, okay, because that's going to help us kind of understand these theorems maybe a little bit more. Have we done synthetic division before? Okay, do we remember the setup? Kind of what it looks like? There's a box. I've seen it two different ways, okay? So one setup kind of looks like this. Another setup looks like that. Depends on who you have or what you've experienced. You did the first one. I'm used to this one, okay? It's up to you. I don't really care. It should work out either way. So whatever setup you're used to. So what we're going to do is synthetically, aka fake, divide, if you think about kind of a synonym for synthetic. Instead of doing long division, like with numbers, okay, synthetic division you can think of as a fake way to divide or like a shortcut way to divide. And we're only going to be looking at numbers because I know we're working with polynomials that have x's, but we're just going to be working with numbers in this synthetic division process. We'll eventually put the x values back in, okay, but the whole division revolves around numbers. Do we remember what number goes on the outside of the setup? Either the outside over here, or sometimes I call it my little box number if you use this setup. Remember where that number comes from? Maybe? What do you think? Yeah.
From the x minus 1.
Okay. So whatever you're dividing by, that's called your divisor. Okay, you have those different names listed towards the bottom of that chart. Those might come back into memory like from middle or elementary school when you first learned about division and the different names. Okay, so this is your divisor. You want to keep going? It comes from there, but what's the number we're going to use? Good guess. Okay. We're actually going to use the 0 from that divisor. Like what number would cancel out the negative 1 that's in there? It'd be 1, right? So we're going to put that on the outside. All right, so the outside number comes from the divisor, specifically the number that would cancel out or make the divisor 0. The other numbers we're going to write kind of on the inside or after that box outside number are the coefficients from your dividend, okay, the other part of division. But what's a little tricky with this one is that you have to make sure you write them in order. Okay, if you take a look at your polynomial right now, notice how the terms are kind of jumbled. The largest power is not written first. It's actually written third. Okay, so you want to make sure that your polynomial or your dividend is written in standard form. Okay, from largest power to smallest power, nice order of progression. So the first coefficient we would write down is -3. That's the number in front of the x cubed term. The next coefficient would be -2. The next coefficient would be +2. And then the last number we would write is your constant term of 1. Do we remember what that constant term represents on the graph of the polynomial? What was that connection from the other day? Yeah. It's a y-intercept, good, okay? So there's the setup. Notice how we're just working with numbers. There's no x's yet, okay? Do we remember, now that we have the setup, how the division actually is performed, where we go from here? Little gray, yeah? Maybe.
Like the one below the -3, and then add them.
Close, okay? We are going to put numbers underneath here and add them together. It's going to be a combination of multiplying and adding. The first one, though, we just drop the first number underneath that bar. Okay? So what we're going to do is we're going to take that little box outside number times the number underneath that bar. So 1 times -3 would give us -3 as an answer, and we're going to write that value underneath the next coefficient that we listed. These are the numbers that we're going to now add together. So -2 plus -3 would give us a -5, and we're just going to repeat the process. Okay, box number times -5 would be -5. Add the two numbers together, so we'd get a -3. 1 times -3 is -3, plus 1 is -2. Kind of coming back to us a little bit. Okay, so in terms of division and properly naming these different parts, the x minus 1 is considered your divisor. That's what you're dividing by. Your larger polynomial is considered the dividend. Maybe we'll write that in standard form. So make sure the highest power comes first, and then you progress down from there. All right, so our box number comes from the divisor. The other numbers are the coefficients from the dividend, which means that these new numbers we have from the synthetic division process must be representing the quotient and remainder somehow. Okay, do you want to take a stab at which of these is the remainder, kind of the leftover stuff, and then which one of them represent the quotient? Yeah.
-2 is the remainder.
Okay, so the last number is always your remainder, and then the other numbers are representing the coefficients in your quotient. Now remember, coefficients are numbers in front of variables. So what we're going to do is we're going to start with the remainder and kind of work backwards from there. If the last number is your remainder, the number after that is representing a constant number in your quotient. The number after that is representing how many x's, okay, single x's you have in your quotient. The number after that is representing how many x squareds you have in your quotient. And if we had more numbers, we would just keep going. Okay, how many x cubes we have, how many x to the fourths we have, depends on how many numbers you have in the division. So if we were to write out the quotient with the variables put back into it, it would look like a -3x squared, a -5x, and then a constant of -3. We'll just write down -2 as your remainder. Okay, so the actual division process is just numbers, but you got to go back and put the variables next to those numbers appropriately. Okay, so now that we have all of these different pieces labeled, let's see what the answer to the division looks like. Let me ask you this. If we were to, in a simple number sense, take 11 divided by 2, what do we know that answer to be? However you want to represent it. Good, Kyle? Okay, so we could do 5.5. We could do 5.5 as a mixed number, right? Okay, how many times does 2 go into 11? We have 5 whole times, right? Do we have any leftover? Yeah? Have you guys seen like 5R1 before, like remainder 1? Maybe you haven't. Okay, so you could also represent this as 5 remainder 1. This one is not kind of mathematically appropriate. Okay, usually we have either the decimal or fraction value left, but what we're going to focus on for our answers is kind of this representation. Notice how this 5 is representing your quotient, the 1 is representing the remainder, and the 2 is representing your divisor. You see those values showing up in the division process? So in terms of the answer that we're going to focus on, we're going to take quotient plus remainder over divisor. Notice how if we did 5 plus 1/2, that would be the same as 5 1/2. Okay, so using these polynomials that we did from the synthetic division, we would say our quotient plus remainder, which was a -2, over divisor, x minus 1. Just like 5 1/2 is the answer to 11 divided by 2, this is the answer to the original division we did at the top, okay, through the synthetic process. Okay, let's go ahead and try the next one. Now, is anyone familiar with this setup, or do we prefer the first one? You want the first one? That's okay with me. I really don't care. You might see me do it this way. It's going to work out the same, okay? So if you want to do it the first way, that's fine. What's our little box number from the second example? What is the 0 of your divisor? Yeah? -2. Okay. We then have to take the coefficients from the dividend in order. Okay, so it looks like we have 3x to the 4th. What's our next coefficient? Go, Kyle?
0.
Ooh, why 0?
Because x cubed doesn't show up in the equation.
All right, this is what's a little tricky. So, do you notice how we jump from an x to the 4th to an x squared? Okay, technically you don't have any x to the cubes in there. So you have to show that concept through the division process. You have to use like a 0 as a placeholder. Hopefully this makes sense. Remember when you were like in elementary school using number tiles or blocks? If you wanted to represent the number 105, you would have one 100 tile, you would have 0 10 tiles, and then you'd have 5 1 tiles. Did you guys use tiles? Or bricks or whatever they were? Okay, so in a number sense, we typically use 0 to represent when we don't have anything. We don't necessarily write it in a polynomial because why write plus 0x cubed when that doesn't really affect the problem or affect the equation? So it's not showing up in the dividend, but you do have to show it in the division process. Just like if you were to take 105 divided by something, if you took the 0 out, that's a completely different number. So you have to kind of be leery of those missing terms. Okay, if you don't have something, you got to put a 0 in. So we have 3x to the 4th, so we have no x cubes. Looks like we have one x squared term. We have -3 x's, and then our constant term is a 3. So let's do synthetic division. We'll bring down the first term, and then it's a combo of multiplying and adding from there. Do you guys think you can go on from there? Give it a shot. Can you get those numbers? Work it out? All right. So based off of that, let's go ahead and identify the 4 different parts to the division process. Our divisor was x plus 2. Dividend was also given to us at the beginning. And then based on the synthetic division, we can fill in the quotient and remainder parts. Remainder is 61. And if you were to work backwards from that, you got to fill in the variables for the rest of the coefficients. Okay, so with all four of them identified, we can finally write like the answer or solution to this division. We need the quotient plus the remainder divided by divisor. Do you think you can try one on your own? Maybe try the third one? Okay, whatever setup you like, either the first one or the second one, up to you. Oh, this one's a little different. What's your box number? A half. It's a fraction. Yep. How'd you do? Really good? All right, perfect. So just a little side note here. When you get down here to write your answer, quotient plus remainder over divisor, what is 0 divided by some other number? As long as that other number's not 0, yeah. 0. So if you're adding 0 on the end, you technically don't even have to write that if you don't want to. Okay, you're just going to be left with your quotient. I want to talk about this a little bit further because we're going to highlight this a little bit more tomorrow. If your remainder is 0, what's that telling you? If you have absolutely nothing left over, yeah. It's a multiple. Well, maybe not a multiple. It's a factor. Okay, so your divisor is a factor. Okay, it goes in evenly. For instance, if you did 8 divided by 2, 2 goes into 8 evenly. 2 is a factor of 8. You can do 2 times 4 to get 8 somehow. Okay, so it goes in evenly, nothing's left over. Your divisor is a factor. Okay, so that's something to kind of keep in mind for tomorrow. Okay, so now that we're kind of familiar with synthetic division, we're going to use it to help us kind of draw a connection between a polynomial and a function value. Okay, if you were to plug something into that polynomial, what would you get out? So take a look at the first one in the chart there. If this was your polynomial, find the value of p of 1. Okay, if you were to plug in 1 as your x value, what would you get out? Can we do that kind of quick in our heads? 1's fairly easy to plug in. What'd you guys get? Good call?
Negative one.
-1. Okay, so this is kind of our function value. That's the answer we get out from when we plug something in. Let's see what happens if we were to do some type of synthetic division. So we're going to say that we're specifically looking at the divisor of x minus 1, and we're going to take that divisor and divide it by the polynomial. Okay, so that would be our dividend. So what would be our little box number? What's the special x value from the divisor? Are we thinking 1? Okay, so go ahead and put 1 in your little division setup. And then you're going to use the coefficients from the polynomial as the other numbers. And go ahead and see what you get out from synthetic division. Alright, so when we plugged in 1, we got out -1. And notice how if we use the same value of 1 as the little box number, okay, that little x value that we plugged in before, where's this function value showing up in the synthetic division process? What's special about that number? Yeah. It's the remainder. Okay, so what I want you guys to try are the other 4 examples. Okay, test to see if this relationship happens to be true for some other cases. Okay, if you were to take that little box number and plug it into your polynomial, maybe you get to see if the answer is the same as that remainder. Okay, so go ahead and try the other ones. If you need to use a calculator, that's okay, because in some cases it might be a little difficult. But we're going to plug in, not R. Looks like we'll plug in 2 for the next one. Okay, go ahead and try the other 4. Don't forget the zeros if you need them. Those placeholders. Working out? All right, so what is this relationship? If someone asked you to kind of describe it, I mean, I'm asking you to describe it, but if you were to describe it to someone, what would you say? What do you notice going on between the function values and the synthetic division process? Yeah.
The remainder is equal to the p of that value.
Okay. The remainder is equal to, all right, now he said p of that value. We're going to rephrase that a little bit, okay? I know what you mean and you know what you mean, okay? The remainder is equal to p of dividend 0. Okay, so the remainder is equal to the 0 of the, I think you mean divisor, okay, is equal to the 0 of the divisor when substituted into the function, polynomial, dividend, whatever you want to say. Does that make sense? Okay. So this is kind of our first main theorem that we're going to take a look at for this section. Okay, it's called the remainder theorem. No shocker there, because notice how the remainder is what we're focusing on. So you basically just describe the theorem. If you were to take the 0 of the divisor and plug it into the polynomial, your answer would represent the remainder from the division process. It doesn't tell us anything about the quotient values. Okay, it's just the remainder, kind of the leftover stuff. And that's what we're truly interested in, because what we're going to try to figure out eventually is when do we have a remainder of 0? Meaning, when is a divisor a factor? When does it go in evenly? So this remainder theorem is going to give us a way to quickly check to see if something is a factor or not. If we plug a number in and we get out 0, we know that the divisor of this value is a factor. Okay, so 0 is kind of the special number that we're going to be looking for kind of tomorrow. Okay, it's our little shortcut way. So just as a formal definition on the next page, if a polynomial is divided by some divisor, then the remainder will be the same value, aka equal to, if you were to take the 0 of that divisor and plug it into the polynomial. So if our divisor is x minus a, what's the 0 of that divisor? Yeah, a. So if we were to take a and plug it into the function, that would look like f of a. Okay, we're going to replace every x value with that letter a, whatever it might be. So let's see kind of how this remainder theorem might show up in some questions, for instance. So for what value of k will this function or that polynomial have a remainder of 8 when divided by that divisor? I know they use the word factor there, okay, but factor can also mean kind of a general term meaning a grouping. So I don't want you to get too caught up in the fact that they use factor. That might not necessarily mean a remainder of 0, because notice how we're looking for a remainder of 8. You see that? So the fact that they use that word might not necessarily mean it goes in evenly. A factor is another term for just meaning a grouping or a set of values. Okay? So let's go ahead and use this remainder theorem. What is the 0 of that divisor? X is, yeah, -2. Okay, so according to the remainder theorem, what we discovered on the last page, if we were to plug in -2 into all of those x's in the polynomial, what would our answer represent? maybe you got to flip back to the other page, okay, when we did that whole chart. If we plugged in -1, well, maybe that's a bad example because we get the same thing out. Okay, we'll try the next one. If you plug in 2, you get out 11. What did that 11 represent? 11 was, yeah, the remainder from the division process. Okay, so if we were to plug in -2 for all of these x's, okay, maybe we'll actually show that concept. We'll plug in -2 for all the x's. Our answer would be the remainder from the division process. And what do we want that remainder to be in this particular case? Yeah. The x value is -2. What's the remainder though? We want this to have a remainder of what? 8, exactly. Okay, so when we plug in that value of -2 for all the x's, we know that we should have a remainder of 8. We don't know what the other quotient values are, okay, but we specifically know what the remainder is. So notice how when we plug in those pieces, okay, according to this factor theorem, the only piece we have left to kind of figure out is that k value, and that's what we're trying to do. So let's go ahead and try to solve for k here. Let's see, -2 cubed is -8. Times -2 is a +16. -2 squared is 4. Times -2 is a -8. We then have a -2k, and then -2. So maybe combining some like terms. 16 minus 8 minus 2, we got 6. Subtract the 6. Divide -2. Looks like our k value is -1. So in order for this polynomial to have a remainder of 8, when specifically divided by x plus 2, the k value would have to be -1. Okay, if it was anything else, the remainder would not be 8. Okay, so the remainder theorem tells us if we were to take the 0 from the divisor and plug it in for every x in the polynomial, our answer would represent the remainder from that division process. So instead of going through all of that synthetic division, we can just plug in some numbers and kind of solve from there. Okay, a little quicker, I think, for us to do. Let's try another one. Find the value of k so that this polynomial has a remainder of 4 when divided by that divisor. So what's the 0 of that divisor? Our little box number. Yeah, 3. Okay, so according to the remainder theorem, if we were to plug in 3 for all of those x's, our answer would represent the remainder from a synthetic division process, which we know is 4. So we're going to solve for k from there. Kind of simplifying. 3 cubed, 27, times 3, 81. And then 9k minus 5. So we get -8. Does that sound about right? Alright, can you guys try the last one? Very similar question. For what value of k will that polynomial have a remainder of 0? aka nothing left over? How does negative 9 sound? Good? All right. Let's throw in kind of a kicker at the bottom here. Suppose the function g is divided by this divisor, okay? Which is greater? Okay, the value of g of negative 2 or the remainder when you divide it by that divisor. Okay, so we kind of have to find two things here and then compare them because they're asking us which one is greater. So let's maybe tackle the first one. The value of g of negative 2. What's that telling us to do? What does that notation symbolize or represent? Yeah.
Plug negative 2 into x.
There you go. We're going to plug in negative 2 for all those x's and see what we get. Oh, brother. It's 12. Negative 8 times negative 2 is positive 16. Negative 6 is 2. 38 minus 8, we got 20. Alright, so if we plug in negative 2, we get out 20. That's our first value. Let's check out the other one. We also got to figure out what is the remainder when g of x is divided by this x minus 2. What do you want to do to figure out that value? You could tackle this two different ways, yeah.
Plug into.
Okay, so if you were to take the 0 from that divisor, which is positive 2, and plug that in to the polynomial, we know that whatever number we get out should represent the remainder, okay? What you could also do is maybe you didn't want to go through that remainder theorem process, okay, that connection. You could synthetically divide if you wanted to and just check out the last number at the end. Okay, if you're more comfortable using synthetic division, that's always an option too. But I think some of us might prefer plugging in. Is that a correct assumption on my part? Instead of going through synthetic division, you'd rather plug in a number? Okay, so let's go ahead and plug in 2 and see what we get. Can we get 0? Okay. Which one's greater? G, there we go, greater. Sounds good, guys.
That's one.